Well, guys, good morning. So we're going to start here, but as you're sort of reconnecting with your homework from last time, and well, actually many things. First of all, Donnie, who's not here, sent me an email last night at like 10 o'clock. Guys, I totally updated the website on Friday and then forgot to hit update. And so if you were looking at the homework trying to find the answers, Donnie finally reached out to me for me late last night, which was fine, and said, hey, this stuff's not there. That was, sorry, it's there now, obviously. But guys, as we're getting started, I think there's probably two things on your mind that maybe even supersede this. One of them are the tests that we need to get rewritten. I'm going to give those back to you at the end of the day today. And then the other is I updated everything in third period, all of the labs. And some of you are now like, oh crap, I'm missing all this stuff. Guys, we're going to be fine, but we're not going to talk about it till third period. So just trust me, we'll be okay. Let's do this first. So guys, with that said, this is this crazy catch-all of acid and base stuff. It begins with definitions and it ends with math. The math that it ends with is all leveraging the idea that the molarity of the bits in an acid are the same as the molarity of the acid if it's a strong acid. So if you've got 1 molar HCl, you've got 1 molar hydronium ion. Because it's a strong acid, it completely breaks apart, and so all of the hydrogen goes to hydronium. So guys, based on all of that, lots of stuff in between, conjugates, pH scale. What do you want to talk about? Go ahead, Emma. 2C. 2? Was the... Oh, I just didn't start at the beginning. Oh, okay. Yeah. So, guys, looking at question 2C, I don't know why I always seem to start this without my book. Okay, so guys, looking at question number 2, it's relative to a picture. Do we need to do A and B, Emma, or do those stand by itself? Does C stand by itself? Okay, so it says the following diagram represents aqueous solutions of 2 monoprotic acids. So where A, X, or Y. What is that? Oh, I see. Okay. Then it says the water molecules have been omitted. Which is the stronger acid? Were you okay with that one? So the one that makes the most hydronium, so that would be the one on the right, HY. Okay. Then it says B, which is the stronger base? So let's talk about that. So we understand that we think of the strength of an acid as being opposite the strength of its conjugate base. And so we know that HY is a stronger acid, which means that Y is a weaker base, because if it were a stronger base, it would go backwards and it would weaken the acid. Should we talk more about that? Because HX is the weaker acid, it will have the stronger conjugate base. No, so that's, did I just answer the question backwards? Which would have, no, wait. So, which is a strong, okay, so let's talk about it generically. So, guys, the idea is this, that if we've got some acid, HX, which breaks into protons and then breaks into X or Y or whatever. If this is a strong acid, it does this completely. And the reason is because X is a worthless, I'm sorry, this is negative. Holy smokes. Yeah, my bad. So, guys, the reason that HX is a strong acid is because X is a worthless conjugate base. The actual term is of negligible strength. We're going to talk more in a couple days. But if this is strong, that has no ability to be a base. Then as this becomes a better and better base, this becomes an equilibrium that lies more and more to the left. So functionally, their strengths are opposite each other. So the stronger the acid, the weaker the conjugate base. Is that okay? So then you want to talk about C. So C says, if you mix equal concentrations. Oh. Okay, so this is a little bit of foreshadowing to Thursday. This is all about buffers. So let's talk. It says, if you mix equal concentrations of HX and NaX, will this equilibrium mostly lie to the right or to the left? So here's the idea. So let's scratch this down. So we've got HX plus Y negative, and that had better be in equilibrium, and it is, with HY and X negative. So we've got an equilibrium that looks like this. And then the question is, so say this comes to equilibrium, and then the question is, what happens if we dump in NaY? Well, where does Na show up in this equilibrium? It doesn't. It's a spectator. But Y does. So if we dump in NaY, functionally what we're doing is increasing the concentration of Y. So which direction does Le Chatelier's principle say the equilibrium will shift? Right or left? To the right. Yeah? So guys, if this goes up, same side does the opposite, opposite side does the same, and that shifts the equilibrium to the right. Is the answer wrong? No. Yeah, no, well, here, maybe I'm missing something, but it says our stronger acid-base pair as such. No, that's not, it's this one, right? No, that's not right. That's wrong. It'll shift the equilibrium to the left because we're adding. Yeah, no. Thank you for, guys, I've got here, that's 16.2C. I just need to change that. That's wrong. You're adding an ion that shifts the equilibrium to the right. So, guys, sorry, that one's not correct. Okay, 16.2C. Yeah, Emma, thanks for catching that. Guys, anything else you want to talk about? Y'all good? We're okay? Oh, please. Hold on. Talk to me about what you're thinking.
Not exactly sure.
No. Last time you were writing on the board.
No, when we were doing it, though, we used these and we counted how many.
Right.
So there's like, because you want HY and X minus, so there's two I don't remember exactly. There's like 8 reactants going one way, so there's more reactants than products. There's more groups of this than groups of this if you put these together. So that's how we got it. And we didn't talk about buffers or whatever.
Oh. Hey guys, I may have just got ahead of myself. You know what, gang? This is not Le Chatelier's principle at all. You know what, Daniel, thank you, and Josh, if you played a part in this, I think that I was understanding the question wrong. That really all they're doing is they're saying you've got a bunch of HX and you've got a bunch of Y. Which side does the equilibrium lie towards? Wait, how are you saying that it's to the right? Or to the left? How are you? Josh, can you help us? Do you want to draw pictures?
No,
okay.
So we're saying reactants were HX and Y minus. So we add up the HX, so there's 4 of them, and the Y minuses.
Okay.
Right here. So there's 4 total of reactants, and then we added the HYs, which were these 2, and the X minuses, which were these 2. So we got 4 products.
Okay.
So we're thinking KC is products of reactants.
Yeah.
So 4 over 8, which is 0.5, which is less than 1.
which would mean that it lies towards, so reactants are bigger, so it lies to the left.
Yeah, that's what we...
Oh. Hey, guys, I think I just figured out my misunderstanding in this. I think the problem that I'm having, if you can see this, and this is just my own not reading this well, I was thinking that this one is reactants and this one is products. This is two completely different systems. Okay, so if it's two completely different systems, so we've got HX, which is the one on the left. Oh, so it has nothing to do with either one of these. It's just saying if this is the reaction, you've got more HX and Y on the reactant side, so it would lie to the reactant side. How did... So we could really answer this question and ignore the picture on the right, right? Right, so you could ignore all pictures because if you've got more HX and more Y, it lies to the left. No.
Man, I'm gonna just say I got this one wrong.
Okay, so let's try this. Guys, I think that this is what Josh is getting at. All you got to do is look at the HX box, and you need to count the participants. So you count up the HXs, you count up the Ys, and then you figure out what there's the most of, and there's more reactant than product in there, so that makes the equilibrium to the left. Is that what you're saying? I think so too. Guys, I think I'm making a pretty straightforward question way harder than it needs to be. Fundamentally, we get this idea, right? If there's more reactant, it lies to the left. If there's more product, it lies to the right.
Okay, cool.
All right. Woo! That we understand. Guys, what else? Please. Okay, just a sec. Hey guys, so the question on the table is 43D. Where's it at? Oh, wait. Oh, there it is. So guys, let's take a look at 43D. So guys, question 43D reads like this. So it says, calculate the pH of each of the following strong solutions. Okay. So, guys, let's talk about 43 in its entirety. This, again, is drawing on this idea, and this is important because it's going to change today. So let's build a foundation upon which we can make this change. So we understand that fundamentally, if something's a strong acid, it completely breaks apart, right? Okay. And when it completely breaks apart as an acid, it's completely releasing protons. And then those protons bind to water and they make hydronium. So, with that said, looking at number 43, it says find the pH. But then it says of a solution that is combined, that is made 10 milliliters of 0.1 molar HBr, that's a strong acid, and 20 milliliters of 0.2 molar HCl. So guys, this is the idea behind the calculation. If you watch my hands, maybe it'll help. You got 10 milliliters of one acid, 20 milliliters of the other, you dump it together, what's the pH? Well, pH is a measure of the concentration of hydrogen ion or hydronium. But guys, the trick is this. The first thing we've got to figure out is literally how much hydrogen or hydronium, same thing, is there. So in our HBr solution, we have 10 milliliters. Milliliters to liters, liters to moles, and then moles to moles. And again, this works because these are strong acids. For every mole of HBr, we have a mole of hydrogen ion. So we do that math, and in that beaker, we have 0.001 moles of hydrogen ion. Now we've got 20 milliliters of the HCl. Now we need to know how many moles of hydrogen ion are there. So we do that math, and it's 0.004. So guys, when we dump those together, what that means then is that the hydrogen from the HBr and the hydrogen from the HCl are both available to form hydronium, and the amount of that we have is the sum of these. So molarity is total mole, or I'm sorry, so molarity is moles divided by liters. We have 0.001 moles from this solution, 0.04 moles from that solution, but now the volume's changed. When we start with 10 and 20, we dump that together. And guys, you got to get used to this idea of additive volumes. Stop for a second. This is going to be one of the make or break it things when we're doing titration calculations, is when you are titrating, adding one liquid, adding one solution to another, you are literally diluting that solution the whole time you're titrating because you're draining water into water. And so the additive volume is 30 milliliters, which is 0.03 liters. You do that and we have a 0.167 molar solution, and then you just figure out the pH. So guys, there's a lot of interesting stuff here to think about. Again, strong acids completely give away protons, and volumes are additive, if nothing else. So, Ronnie, was that okay? What else, y'all? Yeah, please. C and D? Okay, so let's take a look. Just C. Okay, so it says, oh no, that's 31. It's at the freezing point. 21. Label each of the following as stronger with strong base, weak base, or something with negligible basicity. In each case, write the formula of its conjugate acid and indicate the strength of that. Okay, so you wanted to look at C and D. So let's do D first, because this is easy fruit. Sorry, that was maybe insulting. But let's talk about it. So on letter D, the idea is this. We've got chloride ion. So from where does chloride ion come from? And the answer is chloride ion comes from the protonation of the acid HCl. Okay, so we know that HCl is a strong acid. And guys, if you haven't committed the 7 strong acids to memory, you have to do that. But HCl is a strong acid. So what does that tell us about the strength of chloride as a base? We're not going to say worthless, we're going to say of negligible strength. So guys, by definition, a strong acid has a conjugate base that has no ability to be a base. So chloride ion is, where did it go here? It is of negligible strength, and and then the conjugate acid is HCl. Is that okay? So now let's do letter C. Was it O2? Is it, but it's O2 minus, right? Oh, it's O2 minus. Okay, so I'll just write it here. So this is O2 minus is the guy that we're looking at. Let's then think about the conjugate acid. So the conjugate acid would then be OH, and that breaks into this and this. And so the question then is, what are the chances that OH is going to function or that O2 is going to function as a base? So taking in hydrogen. And O2 does this like crazy because it then forms OH, which is kind of our definition of a base. So the idea is that O2, especially because of its charge and because of all its unbonded electrons, is really good at hooking up with hydrogen. So that loves to function as a base. But because this is basic, the OH, which is its conjugate acid, would not be basic. Is that okay? Or not acidic, sorry. Right, but that's the next step, which would require a whole nother question to think about that. Go ahead, Meredith. What?
I did this part about, well, I did all of them.
Are you okay now?
Yeah, I just want
Okay.
to think about it.
Sure. What else, y'all? Yeah.
This was a really fast question on 28B.
28B is in boy?
Yeah.
Okay.
Essentially, the question is, why don't we include water in the equation? Isn't it just because water is heating up?
Yeah, but so here's where we're punting. So we said in a heterogeneous equilibria, we never include the solids and we never include the liquids because they don't have partial pressures and they don't have molarities, and that works. What you're going to find is that probably, I would guess even in freshman chemistry next year at university, they'll still go that route. When you get to your junior year, if you're actually studying chemistry and you take this horrendous class, when you get into PChem, which is all the calculus of chemistry, you actually find out that that answer is not fully correct, but for us it's good enough. So yeah. Guys, what else? Y'all good? Oh, Emma. No. 29C. Go ahead. Okay, so this is they love to do this stuff to you on the AP test. They give you a pH, but you need the pOH. They give you a hydrogen, but you need a hydroxide ion concentration. So really, the value of this equation is it basically says if you know one, you can get the other. Right. Right. On 29C, so, yeah, but what did I do? That doesn't look like the right answer. Is that related to an... Because it's not... So... How does that make sense? I don't get it. No, how does that answer the... I don't either. So, a solution in which OH is 100 times greater than H. So the answer should be 10 to the negative fifth, or 10 to the negative, no. Yeah, so guys, help me with this one. And so, guys, here's the thing. If you haven't figured this out yet, I'm wildly comfortable with not understanding things. I'm also wildly comfortable with the reality that I'm not the smartest person in this room. If I am, we're all in a whole lot of trouble. The only advantage that I have over you guys is I've been doing chemistry for decades and you've been doing it for days, right? So I have no problem at all going, and I know that for some of you this sort of like shakes the foundation a little bit. Guys, don't be afraid of saying, I don't know. I don't know. So at some point, this was the answer that I came up with. But you also have to understand that I solve hundreds of these problems every year, and I don't even remember typing this up. So looking back at this now, it's as if I'm really, every time, guys, we answer homework problems, I'm literally doing them for the first time. I don't know the answers. There's thousands of homework questions you guys answer over the year. So it's not like I have them all memorized and I'm just like, hey, yo, let me tell you what's in my brain. I'm literally solving these for the first time every time we get together. So it's really kind of a miracle that this doesn't happen more. I have no idea how I came up with that answer. It makes no sense to me. Because if it's 100 times greater, my thinking is this. We know that these are 10 to the negative 7th when this is just a water solution. So if one of these goes up 100 times, 2 powers of 10, the other should go down by 2 powers of 10. So how is that answer right? Do you know, Max? Oh, right. Okay, because if you were to go 2 powers, the other drops by 2 powers, and now it's different by 4. That's it. Okay, so the idea is that if these concentrations are 10 to the negative 7th, where they're both the same, if one went down by a power of 10, 10 to the negative 8th, and one went up times 10 to the negative 6th, that would give us the split. There you go. Yeah, I was thinking it would change by 100. Each changes by a power of 10, and now they're different by 100. That's it. Yeah.
Well, I don't know if this is legal or if that's but I did like KW is equal to like concentration of H, and then for OH I just plugged in 100 H, and then I kind of
Yeah. Absolutely. Yeah, I think that works great. Yeah. Go ahead.
So I just came at this from a completely different angle.
Okay.
It just says, because the question is it 100
Yeah.
So I just said, 100 times.
Sure. It's got to be basic. But doesn't it also ask you for the molarity?
No.
Oh.
Oh, maybe it does. Oh, it does. Mine did that.
Okay.
My bad.
You guys good? Okay. So, guys, let's transition and let's get into what we're doing today. We'll record. I can't record this homework assignment because Skyward doesn't understand that it's 4th quarter. And this is going to go on 4th quarter's grade. So let's get rid of this. Let's grab a hold of this. Guys, you need note-taking materials and calculators. And we're going to get clipping. Have you guys never really thought about that idea that by far your teachers are not the smartest people in this building? Although, it's actually one of the signs, I think as you become a better and more experienced teacher, you become more comfortable with that. No. So Ellingford's the smartest person on the planet. Yeah, no. So, yeah, no. No, I mean, with the exception of the obvious outlier, which is Ellingford. Right. Yeah, mortal. Yeah. Have I ever showed you guys the trifold pamphlet that I made up presenting the idea that Mr. Ellingford is a walking university and that we should be able to sign up for classes with him? I'll share it with you later. Yeah. Ellingford University. A liberal arts university with a purpose. Oh, yeah. Actually, my favorite class offering from Ellingford was taxidermy. It's a solid choice. Okay, guys, here's what we're doing today. So, guys, prior to today, in our experience, acids are strong and they completely give away their hydrogens, their protons, and they completely make hydronium ion. So, guys, you don't need to draw this beaker, but what we're saying is this. If we've got a 1 molar solution of HCl, we've got 1 molar hydronium ion, we've got 1 molar chloride ion, because strong acids by definition completely break apart. Is that all okay? Okay. Well, guys, today that's all going to change. It's all going to change because we're now going to talk about weak acids and weak bases. But guys, understand, this is where things get weird. Because if we want to find out the pH of this, if we want to find out the pH of this, we just go pH is equal to the negative log of 1 molar because 1 molar acid is 1 molar hydronium. That's not the case when we're talking about weak acids. So guess what we do? Ice boxes. Can't be. All right. So guys, I don't know that you necessarily, I don't think you need, well, don't write this down, but we understand this. We understand this. We understand that weak acids are acids that are not the big seven. They are not the strong acids, but they, by definition, are acids that do not completely protonate in water. Instead, they reach equilibrium. So guys, this is what you need to do in your notes. Please do this. Consider the hypothetical weak acid HA, which kind of brings us back to that question that Daniel and Josh got us thinking about. So guys, if we've got a weak acid HA, please write the balanced equation that represents the protonation of this acid, and do not include water. Do not include water. So guys, from this, you all should have arrived at this. HA in equilibrium with A minus and H plus. What name do we give to A minus? A minus is the conjugate base. Now, guys, when you write this, does it matter which one goes first, the H or the A? It doesn't, but guys, please get in the habit of writing the conjugate base first. It will, you don't need to change it now, but it will make your life so much easier when we start getting into common ion and buffers in chapter 17. So guys, just get used to putting the conjugate base first and then the proton second. But regardless of how you did that, guys, now write the Kc expression for this. So let me catch up and do this with you. So we've got Kc is equal to products, and it doesn't matter which one's first. Like so. Now guys, I know that some of you are getting twitchy because the last time I had you write a Kc expression, it was for the autoionization of water, and we realized we needed to take water out of that because it's a pure liquid. So guys, do we need to remove anything from this Kc because it is either a solid or a liquid and therefore does not have a molarity? No. So guys, let's put this in context. We are now talking about weak acids. And guys, all weak acids are actually crystalline salts dissolved in water. Acetic acid, which is vinegar. I've got a bottle of acetic acid crystals. Guys, lactic acid, the stuff that cramps in your muscles. I've got a bottle of it. It's a solid. Citric acid that that's in citric. Guys, all weak DNA. Guys, all weak acids are crystalline solids that are then dissolved in water. So, guys, you don't need to draw this beaker either, but the idea is that if we've got a beaker of weak acid, we literally have unprotonated acid dissolved in that solution. But some of it protonates, and so we end up with some H and some A. But guys, for the most part, like, we're going to do the math in a minute, but if you've got a bucket of vinegar, like you buy at the store, more than 90% of that vinegar is acetic acid molecules dissolved in water in the unprotonated form. But none of it's at the bottom. It's all dissolved, but not all of it is protonated. Does that make sense? Okay. So guys, this then becomes the Kc for this, but because this is the Kc for an acid, we call it Ka. Oh yeah. Find it on your equation sheet. Huh? There she blows. You guys all got it? Okay. So guys, this is going to become a hugely important value for you as time goes on. This is what is called an acid dissociation constant. And guys, what you're going to find is this screams information to you. So let's talk about it. The larger the value is for Ka, the stronger the acid. Guys, again, the larger the value for Ka, the stronger the acid. And guys, don't let those just be words that you're writing down. Tie it back to this and think about why. If Ka is big, what do we have more of? Numerator or denominator? Numerator. And what's in the numerator? The products, which are the broken apart acid bits. So guys, the higher the value of Ka, the stronger the weak acid. So then guys, the question becomes, what do large Kas look like? And when we talk about large Kas, we're talking about numbers greater than 10 to the negative third. This number will become important to us in chapter 17. But just to give you context right now, when we talk about large Kas, we're talking about greater than 10 to the negative third. So these tend to be small numbers, but still our idea of large is basically kind of revolving around 1,000th. That's a pretty strong weak acid. Okay, so guys, with that said then, we can use this relationship to calculate Kas from pHs and vice versa. And guys, that's what we're going to do right now. Put on your problem-solving hat, and here we go. So guys, it says this. You make a 0.1 molar solution of formic acid. Its pH is 2.38. What is the Ka of the acid? And now guys, here's a brand new idea. What percentage of the acid is protonated? So guys, in order to solve this, think about this. If this were a strong acid, this would be a much more simple problem. Because if we know the molarity, we can directly find the pH, and it would just be the negative log of 0.1. But because this is a weak acid, we're not chasing pH, we're chasing Ka. And in order to figure out this Ka, we need to set up an icebox. So again, getting familiar with the question, we have a 0.1 molar formic acid solution. Its pH is this. What is the Ka of formic acid? And then we'll answer the second part of this question in a minute. So guys, do this with me and let's figure this out. So formic acid is HCHO2. We know that that's a weak acid, so this is an equilibrium process. And guys, now we need to talk about acidic protons. We know that this is an acid, but notice that this thing has got two hydrogens. So which one comes off when this functions as an acid? And the answer, guys, is it's either the first or the last. It's never the one in the middle. So we're going to take off the first, and when we do, this is our conjugate base, and then we've got our protons. Guys, notice that I wrote it conjugate base first. You're going to want to get in that habit. Notice that the conjugate base has a -1 charge because it lost a proton. Now, guys, we need to set up our icebox. So, guys, what do we know? You've done iceboxes before. Most of you did a great job on the last test setting up the icebox. Some of you wrestled a little bit with the quadratic formula. But guys, you're pretty good at setting up iceboxes. So given the data that we've got in this problem, guys, how can we populate this icebox? Let's save that one for last. So we do know the hydrogen ion concentration, but that involves another calculation. What else do we know, guys? The molarity of what? Of the acid when? At equilibrium? No, initially. Guys, we know the concentration of the acid initially. We make a 0.1 molar solution. It doesn't mean that it's 0.1 molar in this because some of it breaks apart. But we started a 0.1 molar solution. Now, guys, what else do we know? Well, we know the pH. We know that the pH is 2.38. But Ronnie, you got to an interesting point. What can we do with that? We can use that to figure out the hydrogen ion concentration. Guys, this becomes really important when you're organizing your calculations. And I'm going to tell you now, some of your icebox calculations on that test were a train wreck because of organization. So guys, what I would do is this. In your notes, I would skip down like 5 or 6 lines. Well, or you could even do it here. Maybe just do it here and then continue down. I'm going to save this space, but maybe right down here, let's find out our hydrogen ion concentration. So we're going to go pH is equal to negative log of hydrogen. 2.38 is equal to the negative log of hydrogen, or the concentration of hydrogen is did you get 0.0042? Yeah? So guys, the molarity of this is 0.0042 molar. Can you confirm or refute that? Is that good? Okay. So guys, this then becomes the question. Where does that fit into our ice box? It's the final concentration of hydrogen. It's the equilibrium concentration of hydrogen. So guys, that number, trying to get some good alignment here, goes down here. That is the molarity of hydrogen ion once this thing has come to equilibrium. But now, guys, think about what we're doing, and we may as well do this now. We're trying to figure out Ka. But Ka will be the concentration of conjugate base ion, the concentration of hydrogen ion, and then the concentration of unprotonated formic acid. And guys, currently, well, I'm getting a little cramped here. Guys, currently we only have one of those. The only thing that we know is the concentration of hydrogen ion at equilibrium. We got to get that entire bottom line. Guys, how do we do it? Go ahead. Yep. The original molarities of these are 0. Now, how do the dominoes fit together? Well, this went up by 0.0042. So what did the conjugate base have to go up by? The same, 0.0042. But then, guys, the acid's concentration went down by 0.0042. So we can then flesh this out. This is 0.0042 molar squared. Is that okay? And then our denominator is 0.1 minus 0.0042, which is 0.0958. So 0.0958 molar. And we do the math, 0.0042 squared, 0.0958. And our Ka is 1.8 times 10 to the negative 1, 2, 3, 4. What do you think, y'all? Do you understand the math? Is that okay? Yeah, please. The subtraction. So the idea is we started with 0.1 molar. We lost 0.0042 molar because we know that's what we picked up in protons. So for every proton we form, we lose one of these. So we subtract, and that's where that comes from. Is that okay? Other things, y'all? Okay, now guys, what we've got to do is we've got to answer the second part of this question. So it says, what percentage of this acid is protonated? Guys, this is not an equation that's on the equation sheet. It's a logical thing that you need to understand. And the logic of it goes like this. The question is, what percent of the acid protonated? Well, guys, if the answer was 100%, we would lose all 0.10 molar. But what amount of this did we lose? We lost this much. So percent protonation is a ratio of protons at equilibrium divided by the number of protons we could have. So guys, I'm just going to do, is it okay if I write down here? Is that okay? So guys, percent protonation is equal to hydrogen ion concentration divided by the acid concentration. Our hydrogen ion concentration is 0.0042 molar, and our original is 0.10 molar, and then this is times 100 to make it a percentage. Is that 4.2 or 0.42? So 0.0042 divided by 0.1 times 100. So guys, that's 4.2% protonated. Is that okay? By the way, guys, let's talk about this. So looking at the Ka value, is this a strong, weak acid? Given the conversation we had a minute ago. Is this a strong, what did we say the cutoff for strong was? 10 to the negative third. We're on the order of 10 to the negative fourth. So this is a relative, it's closing in on strong. It's a fairly strong weak acid. But guys, it's only 4.2% protonated. That means 96% of this acid is floating around in water in its unprotonated form. Only 4% of it's broken apart. You get the idea? Okay. So guys, questions about anything we just did here? Because this is about to get a little interesting. This is fun to teach. You guys good? Okay. Let's do this one. One more to solve, and then amazingly, guys, we're done for the day. What is the pH of a 0.3 molar acetic acid solution? What is the pH of a 0.3 molar acetic acid solution? Switching colors. You guys ready for some icebox? Here we go. So acetic acid is CH3COOH. That's in equilibrium. Guys, again, get in the house. Oh, wait. I was going to ask you a question. Sorry, I already showed you. Which hydrogen comes off? The last one. Now it's on the end. All right. So conjugate base first, protons second, ice box. Oh boy, y'all. We have like unto nothing, right? What do we got? We got 0.3 molar, which goes where? Upper left. Guys, this is all we've got. Now let's do this. What are we solving for? pH. But guys, where in the icebox is pH? Bottom right. So what we want to know eventually is the hydrogen ion concentration, and then we can turn that into pH, right? So we need to get there. But here's what we know. We know that these are 0. And we know, guys, that this acetic acid is going to protonate. And when it does, what's going to happen to the amount of acetic acid, up or down? It's going to go down by how much? We don't know. What are we going to call it? X. So this goes down by X. Guys, what about the acetate ion in the hydrogen? Up by X. Now, guys, here's the beauty of this. These will always just be X's. In these problems, you won't see 2X or 3X. These equations will always balance with 1s. Why? Because they're all monoprotic acids. All right. So, guys, here then we get 0.3 minus X, and here we get X, and here we get X. Some of you are starting to have the quadratic formula shakes. Check this out. Okay, here we go. Ka is equal to acetate ion. I know I'm in the way, but you know what you're doing. Hydrogen ion and acetic acid. Then, guys, our acetate ion is X. Our hydrogen ion is X. And our acetic acid is 0.30 minus X. Are we good? Is that sitting okay? So, guys, now we need to talk. How are we going to solve this for X? What do we have to do? Quadratic formula. No. Guys, check this out. We do not need to use the quadratic formula in order to solve this problem. And the logic behind this, guys, is absolutely brilliant. So, guys, do this with me. Look at the Ka value for acetic acid. What is it? It's 1 times 10 to the negative 5? 5, right? The Ka value is 1 times 10 to the negative 5. Guys, follow this reasoning. If the Ka value for this is 1 times 10 to the negative 5th, about how much of this acid is going to be protonated. To come up with that answer, look at your previous calculation and make the connection. Guys, what is the Ka for formic acid? On the order of what? 10 to the negative 4th. And guys, what percentage of that acid is protonated? 4. So if this acid is 1 power of 10 weaker because of its Ka, how much of this acid will protonate? A tenth? On the order of tenths, right? You see what we're saying? Does that logic make sense? So, guys, here's what we've established. Because the Ka of this is so small, not very much of this acid is going to break apart. Now let me ask you this question. Guys, what in the icebox represents the amount that's going to break apart? X. So, guys, here's what we're saying. This X right here represents what? The amount of acid that breaks apart. And how much is that going to be? Less than 1%. So, guys, what we know is this. The amount that this breaks apart is insignificant compared to the initial concentration. We've got so much acetic acid to start with, and so little of it breaks apart that we ignore the amount of this that breaks apart. Now we don't have to use the quadratic formula. Here's how to represent this. The rest of the work that we are going to do is approximately equal. And now, guys, we just solved this thing for X. And so can you picture doing this? All we've got to do is plug in Ka. And guys, Ka is equal to 1.8 times 10 to the negative fifth. So can you picture this math? Guys, all we've got to do is cross multiply. 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. And then we just multiply that by 0.3. Then how do we solve this for x? Is it fair for me to just say take the square root? So guys, we take the square root of that, and it is 0.00232 molar. So guys, we now know the molarity. So again, what is it that allowed us to get rid of that x? Because x is insignificant. So guys, let me ask you a question. Why did we not get rid of those x's? Why did we not get rid of the x's in the numerator? That's what we're solving for. And these x's are significant because it's the molarity of the hydrogen ion. So guys, compared to none, these numbers are important. But compared to 0.3 molar, this minus x doesn't change anything. So guys, the idea here then is that we get rid of the x. It makes the math totally easier. And now we can figure out x without needing the quadratic. Go ahead. Oh, baby, and you're not going to like it. We'll get there in a minute. So guys, Matthew's question is there a rule for when this x is small enough that it's insignificant? And the rule is actually recursive. I'll share it with you in a minute. It's horrible. So let me show you. So guys, now let's answer the question. What are we solving for? pH. So we go pH is equal to the negative log of hydrogen ion is equal to the negative log of 0.00232 is equal to, take 0.00232, take the log, change the sign, 2.63. What do you think, y'all? You okay on the process? Because the only thing we still need to do today, well, one other brief thing after this, we got to answer Matthew's question. So guys, if you don't understand the question, it's simply this. So we made this, well, let's do it this way. So why did we get rid of x? Because it's insignificant compared to the original molarity. How did we know that it was going to be insignificant? Because we looked at the Ka value, and that Ka value, 10 to the negative fifth, was relatively small. Because it was small, we felt comfortable getting rid of this, and so we got rid of it that way. So guys, the question then, as Matthew said, is when does that not become okay? And guys, the answer is this. If an acid is less than 5% ionized, it's mathematically okay to disregard the concentration due to protonation. Same that we're right. Nathan, your observation is brilliant. Let's talk about why we did that first. If you want, guys, all you need to know is 5%. 5% is the cutoff. But guys, you're going to remember 5%. You need to make sure you understand this idea. Say what you said again. Right, so looking at formic acid, it was 4.2% protonate. Would that have been okay to get rid of the X? Sure. But guys, do you see the problem with this? You have to do the math to figure out if it's okay to have not done the math. Right? Because the only way, guys, the only way to come up with percent protonation, and by the way, we could do that. The percent protonation here is oh, goodness gracious. Look out. Guys, the percent protonation here, let me just go up to right here. The percent protonation here, and I'm just going to chicken scratch it, is 0.00232 divided by 0.3 and times 100. So 0.00232, oh golly, 0.00232 divided by 0.3 times 100. So guys, this is 0.77% protonated. So this is the problem, guys. This is 0.77% protonated, which means it would be okay to drop the X. But the only way to know how protonated it is by doing the math. And technically, to do the math, you shouldn't drop the X until you know it's okay to drop the X. And so basically what you end up doing is solving these using the quadratic, come up with the percent protonation, and then figure out you didn't need to use the quadratic. That's bad. So guys, this then becomes the rule. Oh gosh, it's not there. It's not in my notes. Guys, the rule is this. 0.5 proton or 5% protonation hovers around a Ka value on the order of 10 to the negative third. That's what I was talking about when I shared that value of 10 to the negative third with you. So guys, here's the rule. If you're solving for pH for a weak acid, and if the Ka is 10 to the negative third, you have to use the quadratic. If it's anything smaller than that, 10 to the negative fourth, right, which we verified with the formic acid question, and then anything smaller than that, you're okay to drop the X. So if it's 10 to the negative third or greater, you can't. If it's 10 to the negative fourth or smaller, you can. Oh, if you want to do the quadratic formula? Right, but also understand, Spencer, that you only have limited time to take the test. And frankly, it's a waste of time if you don't have to do it. So, guys, do you get the idea? Okay. So, guys, with that said, there's one more thing that we need to talk about, and it's this. How do we do these calculations with weak bases? Well, guys, let's do this. Weak bases are compounds that do not bring OHs to the table. Guys, we understand that sodium hydroxide is a base because it's got OH. But guys, what about something like NH3? How does NH3 make hydroxide if it ain't got any hydroxide? It attacks water. So guys, do this with me if you would, please. Write the balanced equation for what NH3 does to water. Write the balanced equation for what NH3 does to water. Did y'all get this? And did you notice that I put the conjugate acid first in products? Get into that habit. Now, guys, this. Kb is equal to products.
I don't know. Well, I added it eventually.
But guys, here's the trick. With acids, you can choose to include water when you need. With bases, you include water all the time. Because without water, NH3 can't be a base. So our products then are these. And guys, why did I not put water in the denominator? Because it's water. So guys, find this on your equation sheet. You'll notice how it's written. It is Kb, where B is your base. For us, that was NH3. Can you make the connection? And then what happens is your base picks up a proton, so that would be Hb+. And then you get hydroxide. Notice that's the numerator of your Kb expression. And then the denominator is Hb. Okay? So guys, then the question becomes this. How do we icebox something like this? And guys, iceboxing these are exactly the same as iceboxing acids, with one change, and it's this. You will never have values for the water It has to be there to balance the equation, and you must represent it in the icebox. But literally, guys, when you're building this icebox, I just like to put not even X's here because they look like variables. I just put squiggles here to just go, there are no values in that column because water does not have a molarity. Okay. Then, guys, finally this. This leads us to an interesting idea. So, guys, let me use this as a way to think about this. So this is a base. This is new, guys. Don't miss this. This is a base. What's this? A conjugate acid. Now, guys, back in homework from the previous day, we talked about this idea. As this gets stronger as an acid, what happens to the strength of this as a base? I'm sorry, let me do that's backwards. As this gets stronger as a base, what happens to the strength of this as an acid? It gets weaker. So as one gets stronger, its conjugate gets weaker. And guys, that can actually be represented mathematically by yet another crazy mathematical relationship, which is this. It's Ka and Kb also resulting Kw. This is also on your equation sheet. And guys, let me explain to you what this means. For example, if we have the equation that we just looked at with acetic acid. Guys, we know that this is a weak acid, and we know that this is its conjugate base. But we know the Ka for this. We calculated it. It's 1.8 times 10 to the negative fifth. Because we know that, we can now figure out the Kb for this. So guys, understand when we do this math, this does not mean the Ka and the Kb for acetic acid. It's the Ka for acetic acid and the Kb for its conjugate. And when we do the math using this equation, because Kw is 1 times 10 to the negative fourth, the value is 5.6 times 10 to the negative 10th. So we can leverage that relationship to go from Ka to Kb of the conjugate and vice versa. So guys, with all of that said, here is your homework. And guys, we are now going to go over your tests. So Kaylee, I'm going to get yours to you first. And then you are welcome to go when the bell rings. And then, guys, we are going to bleed a little bit into break. So, guys, as you're looking these over, I need these back from you Thursday. That is a non-negotiable deadline because I need time to get these graded. So I need these back from you on Thursday. But guys, I'm going to ask that you do stay for a couple of seconds into break. And then we'll take a full-length break. Oh, sorry. When we're ready. All right, so guys, I'm going to stop recording. Let me get you your tests. And we'll get out of here in a few minutes.